I... Hello, can you hear me?
Yes, I can hear you.
How are you doing?
Well, and yourself?
Fine, thank you. So tonight, this week, we'll be focusing on, I'll show you, let me open our class. Where is it? This is the class right here. Okay, I'm gonna share it now. So let me show you in my announcement, and like I said, always read my announcements. I put a lot of information there for each week. So we're finishing chapter 4 this week. Actually chapter 3, and we begin chapter 4 this week. So we finish chapter 3, and then we begin chapter 4. So as I wrote here, start reading chapter 4. Then assignments, they have classwork 5, which should be output after this session. It will be due tomorrow. Then complete the homework from last week, homework 3 and 4 by Sunday. And then test 1. And that's it. So actually the assignment that is due this week is just the classwork 5 and test 1. I didn't put Excel assignment because you are going to have your test 1 this week. So test 1 is based on is an open book take home test. So you do it at home. And I did something else. I provided practice test that you can use. You can do it as many times as you want. Let me see if I have it here. The practice tests. Test 1. I haven't put test 1. Let me see if it's here. Yes, okay. Assignments. Let me put it right here. Test 1. Yeah, this is test 1. So they're here now. You can see the practice test. This is practice test. Once you click on it, it will take you to my lab loss. It will be as if you're taking the main test, the rate test. So do it as many times as you want. After this Saturday, it will no longer be available. And then test 1 will be available. Let me just put the test 1 in right away so that it will be there for you. Test 1 is due. It's going to be due on Sunday. So do the practice test. The 7 questions, you have similar questions in your test 1. Just a similar questions. Test 1. That's my attendance paper. Okay. Let's see. Okay. Let me just make it available. Update the date. Test 1. So test 1 will be okay. With 2 attempts. You have 2 attempts. 50 minutes. Okay, and okay. So I'll make it available now. Oh, it didn't change. Well, let me do it again. I think it didn't change. Let me do it again. Yeah. So the due date now will now become September 22nd. Okay. Yeah, we have okay. So I'm gonna close this and then sync this. So it will appear, it will be updated. Sync everything. All right, everything will have been synced. Good, excellent. Oh. Where is my test? Okay. Good, 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 good. All right. So it's a let me share it again. So once you click on the models, you scroll down to model 3, you see test 1 right here. But I will recommend that you do the test 1 review. It doesn't count as your grade, even though it says 17 points here. It doesn't count as a grade. It's just for you to practice, to prepare for the test 1. So do as many examples as you can, but finish it if you can. Finish it so many times. If you can do well in it, then you can do well in test 1. So having said that, let's go to what we have today. So we finished data description today, and then move on to the theory of probability. So let's begin. Empirical rule and Chebyshev theorem. Let's start with empirical rule. The empirical rule, according to the empirical rule, for data set having a distribution that is approximately normal, So for that data set that have that kind of distribution, the following properties hold. Let me make it a little more bigger. The following properties hold. Make it 16. It says about 68% of all data values fall within one standard deviation of the mean. About 95% of all values fall within 2 standard deviation of the mean. And about 99.7% falls within 3 standard deviation of the mean. What does that mean? What are we trying to say here? We look at, remember, this is for empirical rule. The data set must be bell-shaped, normal, or symmetric. So that means if it doesn't have all these qualities, it means that you can't use empirical rule for it. So there's a chart. We did this we have looked at this kind of chart before when we did shape of distribution. These numbers are set on stone. Now let's explain again. It says here about 68% of values fall within 1 standard deviation of the mean. Look at this data set. You can see this. You can see that it's a bell-shaped, and you can see that we have mean right here. The center is the mean. On the right side, we have +1 standard deviation, +2 standard deviations, +3 standard deviations. On the left side, you have -1 standard deviations, -2 standard deviations, -3 standard deviations away from the mean. And we have this numbers 34, 34 that has put in for this kind of distribution. So like I said, these numbers are set on stone and they are computed by statisticians using different formulas. And I'll give some formulas which I will explain in a minute. It says here about 68% of all value fall within one standard deviation of the mean. Now look at one standard deviation of the mean right here. You can see it right here on the left side and on the right side. So that we have, this is one standard from here to here. Okay. So it's a 68%. So if you add these two numbers, you will have 34%. Excuse me. It's okay. Let me do it in a different way. It says here 68%. Since there are two sides, the left side and the right side, so you're gonna be 68% divided by 2. I'm talking about for one standard deviation of the mean. So if you divide 68 by 2, you're gonna get 34% on both sides. And you can see right here, 34, 34. When you add them together, you're gonna get 68%. And that's what it's saying. And this for the negative sign is just to show that it's on the left side. And this is for one standard deviation and the left side and one standard deviation on the right side. Now, for the other one, it says about 95% fall within two standard deviation of the mean. Okay, 95%. So now we have 68% already, right? So if you have 95%, 95, if you do 95 minus 68 that we already have, and then divided by 2, we have, I'm going to take it to 95 minus 68 divided by 2. Where are all my calculators? Okay. My calculator, okay. You have, we got 95 minus 68 divided by 2. You give me 13.5%. 13.5% on both sides, 13.5%, which you can see here on the left side and on the right side. And that is for two standard deviations of the mean. See? And then for the for three standard deviation, it is 2.35% and 2.2%. And according to empirical rule, it says about 99.7% of all values fall within three standard deviation of the mean. So if you do, since now we have 95, now if you do 99 point, if you do what number? 99.7%, 99.7, you got let me go this way. Since we have gotten 95, 99.7%, okay, 99.7 minus 95 minus 95 divided by 2, because it's two sides, left side and the right side, okay, left side and the right side. So you have, taking you to the calculator, we have 99.7, we got 99.7 minus 95 divided by 2. Give me 2.35%. 2.35% on both sides. 2.35% on both sides. And you can see it on the chart, 2.35% on the left side, 2.35% on the right side. And that is for three standard deviations. So that is what Chebyshev is saying. So that is what empirical rule is saying. for the data set that is bell-shaped, normal, or symmetric, about 98% of the values lie within one standard deviation of the mean, which you can see from here. 68% divided by 2, you have 34. And this is within one standard deviation of the mean. The next is that about 95% of all values fall within 2 standard deviation of the mean. So if you add from here, if you add from this point under 2 standard deviation to the next 2 standard deviation on the right side, you get 95%. And so on and so forth. So for 99.7, you're going to be add from this point from this 3 standard deviation on the left side to the 3 standard deviation on the right side. That will give you 99.7%. So you use empirical rule if and only if the data set is bell-shaped or symmetric or normal. See, if the question doesn't say that, that means you can use empirical rule. Now, another thing I want to show you about empirical rule is this. I haven't have it here. It said, let's look at unusual. Data entries that lies within more than 2 standard deviations of the mean are considered unusual. I'll give you an example. We know that we have a normal blood glucose level. There is a value that is considered normal. Now, if it is higher than that value, that means you are diabetic. That means that's abnormal, not normal. If it's too lower than that, as can also be considered not normal. So those values fall outside 2 standard deviation. But values that fall within more than 3 standard deviation are also considered very unusual. But so long as it falls within 2 standard deviation, make sure I've seen this. So long as it falls within 2 standard deviation, here, from here to here, it is considered usual. But if it falls outside that, like from here, on the 3 standard deviation on the left side, more than 2 standard deviation on the right side, left side and right side, is considered unusual. So normal range is when it fall within 2 standard deviation on both left and right sides. Okay. One more thing is there's a formula that we need to use when we do problems involving empirical rules. In general, we use the following equation to express the range of values of K, standard deviation around the mean, which is mean plus or minus K times standard deviation. On the left side, we use negative sign. So that means left side will be mean minus K standard deviation, where K represents the number of standard deviation away from the mean. On the right side, we use plus. That means mean plus K standard deviation of the mean. Okay, this is the, so I've given you the background for empirical rule. Now, let me give you background for Chebyshev. For Chebyshev rule, we use Chebyshev for any distribution. Remember, empirical rule can only be used for a distribution that is normal or symmetric or bell-shaped. So if it's not those things, you can't use empirical rule. But the Chebyshev can be used for any distribution, provided that the data set lie within K standard deviation, where K is greater than 1 of the mean. So we use this formula, at least 1 minus 1 over K squared times 100%. Okay. Now, according to Chebyshev, look at what he says. He says here that at least 75% of data values fall within 2 standard deviation of the mean, around the mean. At least 89% of the data values fall within 3 standard deviation of around the mean, and then at least 94% of the data values fall within 4 standard deviation of the mean. So, like I said, it can be used for any distribution. Now, again, just like the empirical rule, we use the same equation, which is mean minus K standard deviation on the left side and mean plus K standard deviation on the right side. But we can use, before we can use that, we have to compute K. And this is the formula for computing K. Remember that K is the number of standard deviations around the mean. We can use K equals to upper end minus mean divided by standard deviation, or you can use K equals lower minus mean divided by standard deviations. I know this might sound like gibberish to you, but as soon as we start using it, applying them to solving problems, yeah, it will be more clear to you. Excuse me. Also, let's begin. Let's try the first example. The first example says, past results have shown that, according to past results have shown that from the National Health Survey, suggests that the pulse rate, when we say pulse rate, we mean heartbeat per minute, of women have a mean of 76 and the standard deviation of 12.5. Assume that the distribution is symmetric. So we said assume that it's metric. That means we can use empirical rule on this. If it doesn't say this, then you can use empirical rule. It's a find the minimum and maximum usual rate, pulse rate for women based on this information. So find the minimum and maximum usual pulse rate for women. Then determine the whether a pulse rate of 110 as 110 heartbeat per minute will be considered unusual. So first thing is to write out your mean. You say that mean is 76 and the standard deviation is 12.5. So we get the minimum value and the maximum value. To get the minimum value, we use this formula here. Mean minus 2 times standard deviation. Why do we use 2 here? Because I told you a few minutes ago that when it is within 2 standard deviation, it is considered the usual rate. So that's why we use 2 standard deviation here. So because data entries that lie within 2 standard deviation are considered the usual. So you have mean minus 2 standard deviation, which means our mean is 76. Put 76, okay, minus 2 times the standard deviation of 12.5. Okay, this is times. If you don't, this is times. Okay, just like this one. This one is also times. Okay, so I'm gonna put this in the calculator so you can get the result. Let me write it down first. That's my book. So I got 76 minus 2 times 12.5. I'll give us the minimum side. Clear this. 76 minus 2 times 12.5. Give me 51. So I go back there and put 51. 51 beats per minute. 51 beats per minute. And on the maximum right side, do the same thing, but this time around use plus sign. So I'm just going to copy this and put it here, then change the minus sign to plus sign. Give me the result. So change this to plus sign. So that means gonna change this. So we'll go to the calculator and just change the minus sign to plus sign. Change it to plus sign. It's gonna be give me 101 for maximum is 101. So we're gonna put 101 right there. 101 beats per minute. So that answered part A. Because it says part A say find the minimum and maximum usual pulse rate. That's the minimum which is minimum is 51 bits per minute, maximum is 101 bits per minute. Now, part B says, then determine whether a pulse rate of 110 is considered unusual. Yes, so 110 is unusual because it does not fall. This is the maximum and minimum usual rate for women is 51 to, according to our calculation, is 51 to 101 bits per minute. And so somebody who has a pulse rate of 110 bits, it doesn't fall within this interval. It's bigger than this interval. So it is a pulse rate of 110 bits per minute is unusual because it is it falls outside the range of values. Any question on this? Any question, guys? Okay, so no question. Excellent. Now let's try another example here. It says here that the all right, make it bigger a little bit. Make it 18. It says the mean speed of a sample of vehicles along a stretch of highway is 67 miles per hour with a standard deviation of 4 miles per hour. And it says again, assume that the data set has a bell-shaped distribution. Bell-shaped, see, distribution. So then it says estimate. When you say bell-shaped or symmetric or normal, that means you can use empirical rule. It says estimate the percent of vehicle whose speed are between 63 miles per hour and 71 miles per hour. Then part B says, suppose that the number of vehicles in the sample is 75. Estimate the number of vehicles whose speed are between 63 miles per hour and 71 miles per hour. Then part C says, in a sample of 25 vehicles, about how many vehicles would you expect to have a speed, speed exceeding 71 miles per hour? Let's do it. First thing is to write out this mean and the standard deviation. I have it right here. Mean is 67. Standard deviation is 4. So let's answer the first question. Remember, it was asking, estimate the percent of vehicles whose speeds are between 63 miles per hour and 71 miles per hour. To be able to answer this question, we need to get the answer to all this here. I'll show you this chart before you can see the mean. On the left side, you subtract the one standard deviation, 2 standard deviation, and 3 standard deviation. And on the right side, you add 1 standard deviation, 2 standard deviation, and 3 standard deviation. So let's start with the mean. The mean is 67. And let me write it down. And the standard mean is 67. And standard deviation is 4. So let's put the mean right here. Mean is 67. 67. Okay. Now, on the left side, we subtract 4, which is the standard deviation. So 67 minus 4. 67, we got 67 minus 4 is 63, as you can see. So we're going to write 63 right here, 63 here, 63, and minus 63 minus 4. So you keep subtracting standard deviation. 63 minus 4 should be 59, and 59 minus 4 will be 55. Then on the right side, you add 4. 67 plus 4 give us 71. 71 plus 4, 75. And 75 plus 4, 79. Once you get these values, you can now be able to answer the first question and the third, second, and third. The first question says, estimate the percent of vehicles whose speed are between 63 miles per hour and 71 miles per hour. So you can see that this is 63 miles, right? Let me move this down a little bit. You can see 63 miles right here. And you can see 71 miles here. So we are looking for what we are looking for is the percent of vehicle whose speed are between 63 and 71. And that is very simple. You can look at it, you can see it's 34, 34. So the answer will be equals to 34% plus 34%. That gives us 68%. See? So the percent of vehicles whose speed is between 63 miles and 71 miles is 68%. Okay. Now, the second question says, suppose the number of vehicles in the sample is 75. Estimate the number of vehicles whose speed are between 63 miles per hour and 71 miles per hour. So now we already have their percent as 68%. So that the number of vehicles whose speed, let me make it bigger. Number of vehicles whose speed is between 63 miles per hour and 71 miles per hour. The percent is 68%. Maybe have 68%. Because they told us that the question says that if there's a sample of 75 vehicles, so our N is 75. So N is 75, right? And okay, I'm putting it the wrong way, so let me split this way. N equals 75. You know, the small n equals 75. Okay, which means that the percent of vehicles whose speed are between 63 miles per hour and 71 miles per hour, this is 8% times 75. 71, 75 times 75, which means 8%. When you change it to decimal, you're gonna be 0.68 times 75, and that will give you the answer you're looking for. 0.68 0.68 times 75 is 51. 51. So 51 vehicles. 51 vehicles have the speed of speeds that are between 63 miles per hour and 61 miles per hour. Okay. So that's answered part B. Part C says, if the sample in a sample of 25 additional vehicles, how many vehicles will you expect to have a speed exceeding 75 miles per hour? Okay, first of all, I have to get the percent for that. Exceeding, this is 75 miles, exceeding 71 miles per hour. Okay. Exceeding 71 miles per hour. Good. Now, in this case, our N, I'll make it bigger. 18. So in this case, our N is 25 vehicles. That is small n. N is 25 vehicles. So now the percent of vehicles whose speed are between exceeds 71 miles. So let's get the percent first. Okay. The percent will be it seems 71 miles. This is 71 miles right here. Okay. From here. From this point, it's 71. So exceeding goes from here to this. So this is what we're looking for. That means we're going to add this plus that. So let me write it down. 13.5% plus 2.35%. So that, first of all, you get the percentage. I mean, the percent of vehicles who that have speed exceeding 71 miles per hour will be this first of all, again, is for 13.5%. We got 13.5% plus 2.35%. 2.35%. And that will give you the percent of vehicles that has speed exceeding 71 miles. So let's go put it on the calculator. Okay. I have 13.5% plus 2.35%. You get 15.85%. Get 15.85%. Let's go and put it right there. 15.85%. Okay, 0.85%. So with that, we can now calculate the percent of number of vehicles whose speed exceeds 71 miles per hour. In that case, we're going to do 15.85% times 25, since our n is 25, which means when you change 15.85% to decimal, it's going to be 0.1585 times 25. Let's go and multiply it. I'm going to have, going into the calculator, we have, calculator, I have it right here. Clear this, 0.1585 times 25. 3.96%, 3.96%, yes. 3.96%. 3.96%. Okay? Sorry, not percent. 3.96, not percent. Yeah, 3.96 vehicles. That means approximately 4 vehicles. 4 vehicles has speed that exceeds 71 miles per hour. 3.96 vehicles, or approximately 4 vehicles. Okay. Now that answers the question. Okay. All right. Any question in what I did so far? Any question, guys?
Can you do B again for me?
Huh?
Letter B, the second one.
Second one, yeah. This one here?
Yeah.
So what's the question here? Go ahead, I'm listening.
Yeah, that's the one.
Yeah, what's the question? What do you want to know here?
Can you just redo the problem for me for B?
Oh, yeah. B says, suppose the number of vehicles in the sample is 75. That means our n is 75. Estimate the percent of vehicles whose speed are between 63 miles per hour and 71 miles per hour. So now we calculated that it is 68% here. So to get, since our n is 75, all you have to do is to use 68% to multiply 75. So this 68% times 75. But before we can complete the multiplication, we need to change 8% to decimal, and that gives us 0.68. To change to decimal, normally what you do is to divide by 100. Say 68 divided by 100. That gives 0.68, which is what we used. So multiply 75. So we do that. After we did that, we do the multiplication, we get 51 vehicles. Okay?
Yes, I understand. Thank you.
You're welcome. Now, let's try a different example. Look at this question. It says the average check at a local restaurant. The average check at a local restaurant is $36.42 with a standard deviation of $8.15. What is the minimum percentage of checks between $15.25 and $57.61. Now, it didn't say something like the other one, other ones we did. It says, assume the data set has bell-shaped distribution. It didn't say that. Just like the other one we did here. Say, assume that the distribution is symmetric. This current question didn't say all that. When it doesn't say that, that means you can't use empirical rule, which also means that what we're going to use here is Chebyshev, because Chebyshev can be used for any data set. So first thing to do is to write our mean. Mean is $36.42, and the standard deviation is $8.15. And they're asking you, what is the minimum percentage of checks between $15.25 and $57.61? To do that, we need to find the care. Then we use the care to calculate the percentage. So now, to do that, we already have our mean and the standard deviation written out. So it says here, what is the minimum percentage of checks between $15.25 and $57.61? So the upper range is $57.61, and the lower range is $15.25. So we use these formulas. Either you use this one or use that one. It doesn't matter. Give you the same result. Let's calculate care first. Once we get our care, which represents the number of standard deviations above or below the mean, we can now calculate the percentage. So care, let's try this. Try the upper range first. Care becomes in this case, if you're using the upper range, care becomes, remember the formula says upper minus mean divided by standard deviation. So upper is 57.61, okay, minus mean. Our mean is 36.42, okay, divided by standard deviation. Our standard deviation is $8.15, 8.15. Okay. Now let me write this down so you can get it from our calculator. So we have care equals 57.61 minus 36.42 divided by 8.15. Okay. Equals, let's go and put this on the calculator. So we got 57.61 minus 36.42, okay, divided by 8.15. Give me 8.15. Give me 2.6. 2.6. So I'm going to go over there and put 2.6. 2.6. Then as a check, I can do the same thing for lower ends. I use K equals to lower minus mean over standard deviation. So we have, and our lower side is $15.25. So $15.25. Okay, minus mean of $36.42. Okay, divided by standard deviation of $8.15 equal. So let me write this down so you can just go and get it. Okay, it becomes $15.25 and $36.42 divided by $8.15. So we'll go over there. Just change this to $15. $15.25, since the mean is still the same. I got negative 2.598. Negative 2.598. Let's go and put it there. which is negative 2.998 8, which care is usually written as in 2 decimal place or 1 decimal place. So this is approximately negative 2.6. So you can see that it is the same. We got the same answer, 2.6. One is negative because it's on the left side. That's what it means. So with this now we can find our percent. But remember what they're asking us was to find the minimum percentage of checks. Okay. So now to find the percentage, we use this formula here. Okay. 1 minus 1 over k squared times 100. So I have our k as 2.6. So you can now have this as the minimum percentage will be using this formula here. Make sure you are seeing this. So we're using this formula here. Then the minimum percentage will be since our k is, remember that our k is, okay, excuse me, is 2.6 or negative 2.6, whatever it is. We have it here already. Let me make it big, make it 18. Okay. So that means the minimum percentage now becomes I'm gonna write it with a marker. It's gonna be 1 minus 1 over 2.6 squared. Okay. Times 100. Okay. Percent. See? And that will give us the answer we are looking for. Let me write this down. We got 1 minus 1 over 2.6 squared times 100 cents. So let's go and have this put this in the calculator. So we got 1 minus 1 over 2.6 squared times 100 give us 85.2%. So our answer becomes 85.2%. That's the answer right there. So that the minimum percentage of checks between $15, 25 cents and $57 at 1 cent is 85.2%. Any question on this one? Any question? Excellent, excellent. So now let us look at another example. It says here, for a symmetric bell-shaped distribution, for a symmetric bell-shaped population with a mean of 20 and the standard deviation of 3, what interval would contain about 95% of the values? Now, let's see. Look at this. You can see that from here, according to empirical rule, empirical rule says, let me take you back to where you have empirical rule. It says that, according to that rule, that about 95% of data values fall within 2 standard deviations of the mean. So having that in the mind, that it is 2 standard deviations, we can now be able to answer that question. It says here that, in 1 minute, it says, for a symmetric bell-shaped distribution, bell-shaped population with a mean of 20 and a standard deviation of 3, what interval contain 95%? So first of all, we write our mean and the standard deviation. So from what I just showed you, you have seen that it is 95% fall within 2 standard deviation of the mean. So that means we're going to use this 2 standard deviation. Left on the left side, we use negative minus 2 standard deviation. On the right side, we use plus 2 standard deviations. So let's do it. We have a mean, we have a standard deviation of 3. On the left side, lower interval, we have a mean of 20. We're going to have mean of 20 minus, I'll make this 18 so you can see better. Okay, minus 2 times the standard division of 3. So if you with 20 minus 2 times 3 on the left side, let's go and put this on the calculator. You got 20 minus 2 times 3 give us 14. 14. I have right here 14. On the right side is do the same thing. Upper interval, do the same thing, but this time use a plus sign. So I'm going to copy this and change this to a plus sign and go to the calculator and change this to a plus sign as well, which is to give me 26. So I'm going to go there and put 26. 26. So which means that about 95% of the values are contained in the interval 14 to 26. Any confusion here? Any question? All right, there's no question. Good, excellent. Now let's move on to the last question on this. We finish this chapter. After this question, we finish the chapter. Then we can now begin probability theory. The question goes this way. It says, assume that the in 1 minute. Okay. It says, assume that the average age of MBA students is 31.6 years old with a standard deviation of 2.6 years. So calculate the z-score for the MBA student who is 28 years old. Then B says, using the empirical rule, determine the range of ages that will include 99.7% of the students around the mean. Part C says, using Chebyshev theorem, determine the range of ages that will include 94% of the students around the mean. And this says, using Chebyshev theorem, determine the range of ages that will include at least 80% of the students around the mean. So first is to write our mean and standard deviation. We have it here. Mean is 31.6 years, and the standard deviation is 2.8 years. Part A says, calculate the z-score for the MBA student who is 28 years old. In that case, our X is 28 years. So to find the z-score, we use this formula here. You can see the formula right here. Z equals X minus mean over the standard deviation. So our S is 28 years. So you're gonna have this 28. Okay. Just 1 minute. 28 minus mean of 31.6 divided by our standard deviation of 2.8. Okay, let's put this calculator. I got put this on the calculator. I got we'll translate this. That 28 minus 31.6 divided by 2.8. Okay. So you got 28. Minus 31.6 divided by 2.8. That give me negative 1.29. Negative 1.29. What this means that the age of this student is because it's negative, that means it is below average. So the age is 1.29 standard deviations below the mean age. That's what it means. Part B says, using empirical rule, determine the range of ages that will contain 99.7% of the students around the mean. According to the empirical rule, it is 3 standard deviations that will contain it. According to the empirical rule, about 99.7% of all values fall within 3 standard deviations of the mean. Again, our mean is still the same thing, 31.6 years, and the standard deviation is 2.8 years. So let's use it. For the left side, we have mean minus 3 standard deviation. So mean is 31.6 minus 3 times standard deviation, which is 2.8. So let me write this down. I got 31.6 minus 3 times 2.8. So we got 31.6. Put it on the calculator. So we got 31.6. 31.6 minus 3 times standard deviation of 2.8. That give me 23.2. 23.2 years. So we go and put it in. 23.2 years. Okay. Now we'll repeat the same process for the upper range. I said that this time around we use plus sign. So I'm going to just copy this and put it right here. And then change the minus sign to a plus sign. Okay. So we can get a different answer. Change this to a plus sign. And I want to do the same thing in the calculator. Go to the calculator and change the minus sign to a plus sign. Give me 40. 40 years. 40 years. That's 40. Which means that the range of ages that will contain 99.7% of the students around the mean is 23.2 years to 40 years. Okay. Yeah. Now, part C says, using Chebyshev theorem, determine the range of values, the range of ages that we include 95% of the students around the mean. Well, what does Chebyshev say about 94%? Let's see. I'm going to take you down up there. So Chebyshev says at least 95% of the data sets, he said 95% of the data values must fall within 4 standard deviations. That's what he says. So we're going to use that. 4 standard deviations. So we have it here. According to Chebyshev, at least 95% fall within 4 standard deviations of the mean. Remember that our mean is still 31.6. And the standard deviation is still 2.8 years. So we're going to use that. So mean minus 4 times standard deviation becomes 1.6 minus 4 times standard deviation of 2.8. Okay. Yeah. So we have it. Let me write this down. Put equal sign. So we got 1.6 minus 4 times 2.8. So we got 1.6 minus 4 times 2.8. Give me 20.4. Yes. 20.4 years. That 20.4. Let's go and put it in. 20.4 years. Then we'll repeat the same process for the upper range. The same thing. I'm going to copy this and then change the minus sign to plus sign for the upper range. That's the only difference. So I'm going to go to the calculator and do the same. Change the minus sign to a plus sign. Okay. Give me 42.8. 42.8 years. So I'm going to type it in. 42.8 years. Which means that the range of ages that will include at least 90%, so at least 94% of the students around the mean is 20.4 to 42.8 years. So that answered that question. So now the last question on this side is, it says, using Chebyshev theorem, determine the range of ages that will include at least 80% of the students. What does Chebyshev say about 80%? Chebyshev didn't say, see Chebyshev theorem. It didn't say anything about 80%. It says something about 75%, 89%, and 94%. Not about 80%. So that means we have to estimate our care by ourselves using 80%. So that means we need to use a formula. We're gonna use this. Okay, 1 minus 1 by care squared. Okay. So we're gonna estimate our care using this formula. Since it doesn't give us the upper end and lower end, because that's what we're looking for, the upper end and lower end. So we're gonna just use this formula to estimate care. So our formula is 1 minus 1 by care squared. That's 100%. But this time they give us, they give us the percentage as 80%. So what we're going to do is to use this formula. We have write it as 1 minus 1 by care. I'm gonna write it. Yeah. So you have 1, okay, minus 1 over care squared. Okay, equals 80%. Okay. So what it says, which means that put it in another form, gonna be, let me clean this because okay. This means that 1, after you remove the bracket, the parentheses, minus 1 over care squared. Okay, it's care. I gotta clean part of this care. Okay, they write it very well. Care squared equals, if we change 80% to decimal, You're gonna be 0 point. Okay, 0.8, right? If you like, you can call it 0.80 if you like. So I'm gonna create more room here. So we solve this. And to solve this, we need to remove make this part to start, from your algebra class. You need to make this one, this part to stand by itself. So we need to remove 1. So you're gonna do -1. And what you do on one side, you must do on the other side. -1. Okay. Our answer will now become 1 is gone. So we have -1 over k squared equals, now we can do this 0.8 minus 1. We can do that on a calculator. We have 0.8. 0.8 minus 1, negative 0.2. Okay, it's 0.2. So we're gonna go over there and put it right there. Negative 0.2. Okay. Right. Then let's create more rooms so I can just finish this. Now, you need to make them, both of them, positive. For algebra, to make the equation both sides positive, divide by -1. So divide by -1 on this side. Divide by -1 on that side as well. That will give us, if you draw the line, give us 1 divided by k squared equals negative 0.2 divided by -1. Negative divided by negative is positive, but 0.2. Okay. Now, now we get the reciprocal of this. We call it reciprocal. When I say I mean this. Reciprocal, okay, of this. Reciprocal. All right. We mean that you gotta flip this. And if you flip this, you gotta flip this. Remember, this 0.2 is just like saying 0.2 over 1. So if you get the reciprocal of this, flip this, and you can flip this one as well. Anything you do on one side, by algebra rule, if you are solving an equation, anything you do on one side, you must do on the other side. So if you flip this one, it's gonna give you k squared equals, then you flip this one, 1 over 0.2, 1 over 0.2. Okay, which means that k squared equals 1 over 0.2. Let's go and get it from the calculator. 1 divided by 0.2. 1 divided by 0.2 is 5. So you can go and put it back there. 5. So that gives us 5. Okay. Now, to find of course, to find k, to make k, let me write it down here again. Let me repeat it so I can show you. You can help me solve this. So what I wrote here was that k squared equals 5. Now to find this care, find this is square. So find the square root of both sides. And whatever you do here, you do on this side as well. Find the square root of this as well. Oh, I'm gonna write it properly. I'm doing this. So square root of 5. Okay. Now square root of k square is k equals the square root of 5 we can find from the calculator. The square root of 5. Okay. Square root of 5 is 2.24. Okay. All right. Is 2.2. Okay, 4. Okay. So once we get our k, we can now use it to answer the equation, because the equation says all the things we did was to find the k. The equation was using Chebyshev theorem to determine the range of ages that will include 80%. So we use this formula to find our k, which is number of standard deviations. That means our number of standard deviation is 2.24. So that the lower range now becomes, if you remember this, remember that our mean is still 31.6 and the standard deviation is 2.8. Sorry, my mistake. We have this was given, right? So k and standard deviation of our mean. See, how this is, so our k is not, for this time around, it is 2.24. So I'm gonna put 2.24 right here. 2.24 times the standard deviation of 2.8. So if you multiply, let me write this down so we can multiply it. We got 31.6 minus 2.24 times 2.8 standard, you go to our calculator and put it in. We got that 1.6 minus 2.24 times standard deviation of 2.8 give us 25.32. 25.3, basically 25.3. So I'm gonna put 25.3. 25.3 on this side. Then repeat the same thing on the upper range. Since they're gonna be the same thing, it's just that we're gonna put plus sign on that one. So take it, copy it and paste it here, then change this to plus sign. Okay. Then go to our calculator and change it to plus sign as well. Okay. Change it to plus sign. 37.87. 37.87. 37. Basically 37.9. So that means that the range of values that will include 80% of the students around the mean is 25.3 to 37.9 years. Does anybody have a question on this? Okay. Since there's no question, I'm going to close this and then open up the next thing the new topic. So the new topic is on probability. So I'm gonna close this one. Okay. So I'm gonna get a new topic, which is probability. I'm gonna put the winter. Okay. The introduction to probability theory. Good. Okay. Nice. So I'm going to share it with all of you. Let me close this one first. Close this. Yeah. So I can, okay. Now I can share this probability. Now, when we say probability of an event, what we are referring to, this means is the likelihood of that event occurring. The probability of an event simply means the likelihood of that event occurring or happening. In other words, it is a branch of maths that deal with calculating the likelihood of a given event occurrence, which we normally express as a number between 1 and 0. So an event with a probability of 1 can be considered a certainty. For example, when you guys knows about dice and coins, when you toss a coin, the probability that the coin will result in a head or tail is 1. Okay, for example, now I know that I'm going to have this class tonight, and I'm here, and I know I will be here, which means that the probability that I will be here tonight for this class is 1. Okay, now an event with a probability of 0 is considered an impossible event. It cannot happen. For example, the probability that the coin will land flat without either head facing up or tail facing up is 0. Okay. Now, how do we calculate probability? We can calculate it as a, where's my attendance? So you can calculate it as a decimal, as a fraction like this, like 7 over 10, or 7 to 10, or 70%, or 0.7. So as a fraction is 7 over 10, as a ratio 7 to 10, as a percent 70%, as a decimal 0.7. This is just an example with 7 over 10. So at this point, we can really take a quick look at the basic concepts of probability. Okay. Under this, we'll be looking at the first concept, which is probability experiment. Simply put, a probability experiment refers to those chance processes that lead to well-defined result that we call outcomes. For example, flipping a coin is a good example of probability experiments. So if you flip a coin, you can land head or tail. How about dice? When I say dice, I'm sure you guys know dice. I'm referring to this dice, 6-sided dice. Okay. So when you roll a dice, can appear 1 can show up, 2 or 3 or 4 or 5 or 6. Now, many examples we'll be doing on this topic will involve gambling, because actually it is gamblers that actually started using probability for the first time. Eventually, we now realize that it can be applied to other fields of human endeavor. So many examples will be based on gambling. So anyway, buying a lottery ticket is also a probability experiment. Either you win or you don't win. So also is drawing a card from a deck. So this gives an example. Any chance process that leads to an outcome, well-defined outcome, is what we call probability experiment. The next thing is outcome. Outcome simply means the result of a single trial of a probability experiment. Like when you toss a coin, the outcome can be head or tail. When you buy a lottery ticket, there are 2 possible outcomes. Either you win or you lose. When you take an exam, the outcome are either you pass or you fail. And when you roll a dice, a 6-sided dice, the outcome can be 1 showing up, 2 showing up, 3 showing up, 4, 5, or 6. Okay. So now, next thing is the sample space. Now, a sample space to this way. Yeah, a sample space it simply means that there's the set of all the possible outcomes of a probability experiment is called a sample space. For example, when you roll a dice, sample space will be make sure I see this. Roll a dice. Sample can be 1 through 6. And 1 showing up. Can be 1 showing up here. Or 2 showing up. 3 showing up. Or 5 or 6. Now, if you're selecting from the days of the week or 7 days in the week, the sample space, the whole possibility will be either Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. Oh, and Sunday, actually, and Sunday, because it's all the possible outcome. So that means I'm going to change this to and. Okay, and so it's all the possible outcomes of a probability experiment. So we can use something that we call tree diagram to also to generate the sample space. A tree diagram simply means a visual way of displaying the outcomes of a probability experiment. So let's see how you can use it. Look at this question. It says, find the sample space for the gender of the 3 children of a couple. Use a tree diagram. In this case, we can say, okay, let's say that we use B for boy and G for girl. Now I can say, okay, let us use a tree diagram to do this. The first child can be either a boy, let's see. The first child can be either a boy or a girl. See? A boy, or girl. Girl. Now, for the second child, you assign boy and girl to each of these outcomes. So for B, we have boy and girl for B. And for G, you also have boy and girl, boy and girl, or a girl. So you have boy, or girl for this, or girl. Then for this one, you also have boy or girl. Then the third outcome, you assign boy and girl to each of these outcomes. So that we have boy or girl, then for this one also have boy or girl. Then next will be boy or girl. The last but not least is boy or girl. So you have boy here or girl. Okay. Then this one will be boy, okay, or girl. Then this one also be boy, boy or girl. And this one will be also a boy or girl. So now, if you try to get all the, because they said find the sample space. Find the sample space for the gender, okay? Find the sample space. So to get the sample, you have to, let's check all the possibilities here. Now, the first child can be a boy, second child a boy, third child a boy, where we have BBB. Or first child is a boy, second child is a boy, third child is a girl. We have BBG. It can be first child is a boy, second child is a girl, third child is a boy. Okay, BGB. Okay, yeah. BGB. Then it can be first child is a boy, second child is a girl, third child is a girl. BGG. Now, on the girl side, I mean, first child is a girl, second child is a boy, third child is a boy. GBB. Or girl, boy, and girl. Girl, boy, girl. Or girl, first child is a girl, second child is a girl, third child is a boy. GGB. Or it can be all girls, boy, girls, first child, girl, second child, girl, third child. So these are all the possible outcomes of this. If you see any family that have 3 kids, the gender will fall into one of this group, must fall into one of this group, sample space. So that this is our sample space right there. This is some sample, all the possible outcome. Okay. Sample space. So the sample space is how many of them? Count them. 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes. 8 possible outcomes. What sample space is. Any question to this class? Any question? Okay. Excellent. Now, suppose you ask this question. It says, find the probability that the family has 2 girls and a boy. Okay. First of all, let's find the outcome for 2 girls and a boy. The outcome for 2 girls and a boy equal, you can see it right here. 2 girls and a boy. This is 2 girls and 1 boy. This is 2 girls and 1 boy. And this is 2 girls and 1. So BGG, 2 girls and 1 boy. BGG, comma. The other one is GBG, that's 2 girls and a boy. The last one is GGB. Okay. So that the probability of getting 2 girls and a boy, there are 3 possibilities. 1, 2, 3 out of 8 possible outcomes. So that the probability of the probability that they have 2 girls and a boy becomes 3 out of 8. 3 out of 8. That means 3 divided by 8. 3 divided by 8 is 0.375. 0.375. 0.375. Or if you like, you can call it 37.5%. Any question on this? Any query? Okay, excellent, excellent. Okay, next one is let's say I ask you this question. I say find the probability that they have 3 girls. The family has 3 girls. Okay. Let's say I ask you find the probability that they have 3 girls. 3 girls. 3 girls. Just 3 girls. Okay. Now for the outcome for 3 girls. Okay. Outcome for 3 girls. For 3 girls, will be, if you look at the tree diagram, only one have 3 gears, GGG. So you have the arts, GGG, okay? So that the probability of 3 gears is 1 out of 8 possibilities. So we can go to our calculator and put that in. Change this to 1. 0.125, 0.125. There's 0.125. If you like, you can call it 12.5%. 12.5% chance that they have 3 gears. So that the probability that the couple have 3 gears is 12.5%. Again, does anybody have a question on this? Yeah. All right, no question. Good, excellent. Now let's look at events, more concepts. Events. An event consists of a set of outcomes of a probability experiment, and there are 2 types of events: the simple event and the compound event. A simple event have 1 outcome. For example, if you roll a dice and the 6 shows, that means that the outcome is just 6. So it has 1 outcome, which is 6. So it's a simple event. If you roll a dice and the 2 show, that means I have 1 outcome, which is simple, which is 2. Okay, if you are choosing the days of the week and get Monday, again, it is still 1 outcome, which is Monday in this case, which makes it a simple event. Okay. Now, compound events have more than 1 outcome. Have more than 1 outcome. Compound event. For example, roll a dice and get an even number. So that case, have the outcome will be 2, 4, then 6. So you have 3 outcomes. That make it a compound event because it has more than 2 outcomes. Getting the weekend, if you select the days of the week and get the weekend, there are 2 days in the weekend, which is Saturday, Sunday. That makes the compound event. Now, other concept we need to know about probability, we have the what's it called, impossible event that can never happen. In that case, the probability of impossible event is 0. So I have for example, the probability that of getting a 7 in a 6-sided dice is impossible, so it's 0. For unlikely events, the probability is less than 0.5. For example, a high school student who never attended physics class, the probability that he will win the International Physics Olympiad is very unlikely. Then for likely events, the chances are greater than 0.5. For example, getting a H when a coin is tossed. Actually, that one is 0.5 and 0.5. But if you have a qualification and experience, getting the job when you apply for it, when you go to the interview, is greater than 0.5. That is more likely event. At this point, we can now look at the approaches to probability. We have 3 of them: classical approach, or what we call classical probability; empirical approach, or empirical probability, or what we sometimes call relative frequency probability; then subjective approach. The one that we normally use in statistics is these 2, the classical and empirical. The subjective probability, that one is because the name is subjective. We don't normally use it. Politicians, it's very popular among politicians. They give you all these statistics that are cannot really verified. You know, you trying to use it to sway your vote to them. Anyway, classical probability. Under classical probability, we compute the probability of an event using the sample space. So in that case, we already know what the sample space is. For example, a dice have 5, say, let me show you, dice have 6 sides. So sample space is 6. And a card has 32. There are 4 suits in a card, each of them 13, so making it 52. So we use this known sample. Days of the week have 7 days. A week have 7 days. So we use this known sample space to calculate probability of events under classical probability. And the formula we use is number of ways probability of event E equals number of ways event E occurs, or number of outcomes of event E divided by the total number of outcomes in the sample space. For empirical probability, we don't normally, we don't know the sample space. So we have to estimate the sample space by actually observing the number of occurrences in the event through an experiment, and then calculating the probability from the relative frequency. Like I mentioned a few minutes ago, subjective probability, we don't use it. So we're not going to bother ourselves with that. So let's look at this one. It says, the first question says, find the sample space for the rolling of 2 dice. In that case, 2 dice were rolled. So the first dice has 1 through 6 sides. And the second dice, as dice 2, have 1, 2, 6 sides. So let's see the sample space here. You see the right for the first dice, this one for the second die, 1 through 6. Now, when you throw the dice, on the first dice, you might have 1 showing up on the first dice and 1 showing up on the second dice. That will give us 1, 1. Or you might have 1 showing up on the first dice and 2 showing on the second dice. That means 1, 2. Or you may have 1 showing on the first dice and 3 showing on the second dice. That is 1, 3. So following that method, you get 1, 4, 1, 5, 1, 6. Or you may have 2 showing on the first dice and 1 on the second dice. That will give us 2, 1. Or you might have 2 showing on the second dice and 2 on the second dice. That means 2, 2. Or you might have 2 showing on the first dice and 3 on the second dice, giving us 2, 3. So following that method, we get 2, 4, 2, 5, 2, 6, and the rest of them. And that is the, so when we count them, how many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 18, right? 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So the sample space for 2 dice is 36 possible outcomes. Okay. So that answers the question. So we'll be using this again for solving more questions. Okay. Now, it says here, find the sample space. Find the sample space for drawing 1 card from an ordinary deck. In this case, look at this is an ordinary deck of cards. Have 4 suits, which are clubs, diamond, hearts, and spades. So club, how many clubs do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them. 13. And diamond is also 13. As heart is also 13. Spade is also 13. We add all this. 3 plus 3 is 6, 9, 12, right? 12. Right, 2 carry 1, put here, go. 2, 3, 5, 52 cards. So the sample space for this one becomes 52 cards, 52 sample space. Any question in what I did so far? Any question, guys?
No, sir.
Okay, good. Now let's look at how we can use this to calculate probabilities. Now let's start from the first one. The first one says, a card is drawn from an ordinary deck of its 2 cards. Find these probabilities. A, of getting a jack. B, of getting a 6 of clubs. C, of getting a 6 or a 3. Let's try the first one. First one says of getting a jack. So we're looking for the probability of getting a jack. So equal. Now you go to the chart. How many jacks do we have here? See, this is jack right here. So you have 4 jack, 1, 2, 3, 4 jacks. So that the probability of getting a jack is 4 out of 52 cards. So we got 4 divided by 52 cards. 0.077. We have 0.0769. You know, it continues. So when you round it to 3 decimal places, you get 0.077. 0.077. Or as you can see, it is, you have 7.7% chance of getting a jack. Okay. Part B says of getting a 6 of clubs. Probability of 6 of clubs, that means getting a 6 and a club at the same time. 6 of clubs. Okay. Now you go to the chart. How many 6 of clubs do we have? See, these are the clubs. Only one number. Only this card is a club with the number 6 on it. And there's 1 6 of clubs out of 52 cards. So that the probability of getting a 6 of clubs is 1 out of 52 cards. So if you go to the calculator, 1 over 52 cards. 1 divided by 52 cards is 0.019. 0.019, or if you like, you can call it 1.9% chance of getting a 6 of clubs. Okay. All right. Part C, of getting a 6 or a 3. So we're looking for the probability of getting a 6 or a 3. Okay. Maybe equals to the probability of getting a 6 plus the probability of getting a 3, which means we have equals for 6. How many 6? What is the probability of getting a 6? Go to the chart. This is 6. How many cards have number 6 on them? We have 1, 2, 3, 4. I mean, 4 out of 52 cards have 6 on them. How about 3? You go back and see the 3 right here. How many cards have 3 on them? That's 1, 2, 3, 4 of them again. 4 by 6. 4 out of 52. That gives us 8 over 52. Which we can now do on the calculator. 8 over 52. So change this to 8. 0.154. 0.154. Okay. 0.154. Or if you like, you can call it 15.4% of getting a 3, a 6, or a 3. Any question on this one? Okay, excellent. No question. Good. Now let's do the last example we do tonight before we round up. And the classwork question we come like this. Yeah, classwork for tonight, for this week. It says 2 dice are rolled. Find the probability of getting A, the sum of 7, B, the sum of 9, C, the same number on both dice, D, the sum of 7. So I have shown you how we get this chart a few minutes ago. And the total possibility, if you count all of them, it's going to be 36 possibilities. With this, we can now answer the questions. You say part 1 says, find the probability of getting a sum of 7. So part A, for sum of 7, what are the outcomes? Will be equal. Now look at these outcomes here. 6 plus 1 is 6, 1. 5 plus 2 is give us 7. 4 plus 3 will give us 7. 3 plus 4 give us 7. 2 plus 5, 7, 1.6. So the outcomes will now become, first outcome will be 6, 1, which will give us 7. 6, 1. We got this one, 5, 2. 5, 2. Next will be 4, 3, and then 3, 4. So 4, 3. 3, 4. Next one will be 2, 5. Okay, comma. 1, 6. Okay. And this is the outcome that will give us sum of 7. How many of them? 1, 2, 3, 4, 5. So that the probability of getting sum of 7 will be 6 outcomes out of 36 possible outcomes. 6 over 36. 6. What about 36? 0.166666. So when you round it to 3 decimal places, it's going to be 0.167. 0.167. 0.167. Or I can call it, like, you have 16.7% chance of getting a sum of 7 when you put 2 dice together. Part B says getting a sum of 9. So let's say the outcome that will give us sum of 9. Okay, outcome that give us sum of 9 outcome equals, excuse me, see here, 6, 3 give us 9. 6 plus 3, 9. 5 plus 4 is 9. 4 plus 5 is 9. 3.6 is 9. So outcome will be 6, 3. Then 5, 4, and 4, 5. 5, 4. Okay. 4, 5. Okay. Then 3, 6. So that there are 4 of them that give us a sum of 9, which means that the probability of getting a sum of 9, okay, equals 4 out of 36 possibilities. 4 over 36. So we're going to change this to 4 over 36. Okay, 4. We have 0.111 to 0.111. Okay. Or if you like, you can call it 11.1% chance of getting the sum of 9. Okay. Then next one is the same number on both dice, of getting the same number on both dice. So let's find the outcome for the same number first of all. The same number on both dice gonna be, when we look at our charts, you will see we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So we have 1, 1, 2, 2. 3, 3. 4, 4. 5, 5. Okay, then 6, 6. How many of them? We have 1, 2, 3, 4, 5, 6. So that the probability of getting the same number on both sides will be 6 out of 36 possibilities. 6 out of 36 possibilities. Okay, 6 out of 36. So you got a calculator. 6 out of 36 again. We did it before, actually, matter of fact. 0.167. 0.167. Okay. Now the last one, before we end, will be part D. Say find the probability of getting the sum of 11. So the outcome of sum of 11 is 6, 6, 5, and 5, 6. Only two outcomes. 6 plus 5 is 11. 5 plus 6 is 11. So for the sum of 11, okay, for sum of 11 at D, sum of 11 equals, we got 6, 5, then 5, 6. 6, 5, comma, then 5, 6. Okay, excuse me. So that the probability of getting sum of 11 equals 2 out of 36. Okay, go and check it. 2 divided by 36. Okay, 0.05555. So that means 0.055555. You know, so yeah, to the 3 decimal places we give you 0.056. 0.056. 0.056. Or if you like, and call it, you have a 5.6% chance of getting the sum of 11. So any question on this? Any question before we round up?
No, sir.
All right. After the class, I'm going to put your classwork. Let me check your attendance and then you can leave. Let me put it out. Where's attendance from? Okay, I'm going to put it from here. Maximize this. Okay. Bruce, I got Bruce. Harris. I got Webster. I got Webster. Dumas. Dumas. Who has the name iPhone guest? Who has the name iPhone guest? Yeah. Kimura Dali. I have that one ready. McCoy. Graham. Yeah, got Peacock. I got Peacock already. Coleman. Got Coleman already. Floyd. I got Floyd already, right? Yeah, got Floyd. Zakia. Zakia. This one is Kia. Zakia. Acha. See her name here. Zakia, you there? Zakia.
Are you saying Nakia or
Zakia. Rachel Zakia. Yeah. Yeah. Rachel. All right. Rodney. Rodney.
I'm here.
What's your first name?
My first name is Rodney
Last name?
Jones.
Jones. Yeah, I see it now. Okay. So gross. That make gross. If I have called your name, you can leave.
Did you already say Chantel Brooks?
Bruce, yes, I have Chantel Bruce here.
Okay. Thank you.
Did you say Kimura Daly?
Daily, yes, I have called you. I've checked you already.
Oh, all right.
There's somebody here who has guessed. I don't know who that person is.
Did you say Eddie?
Eddie who?
Eddie Dumas?
Yes, I've checked.
Do you
already.
have Rachel Parrish?
Parish? No, I don't. That's the one I think. Yeah, I have it now. All right, guys. See you guys.
Did you say Jasmine?
Just now, what's the last name again? Jenkins, right?
Yes.
Yeah, I got you already.
did you say Peacock?
I got Peacock already.
Do
Yeah.
you got Thompson?
Who?
Thompson?
Thompson. What's the last name?
Thompson. My first name is Dante.
Okay, I got it now.
Okay.
All right, guys. Enjoy your week. Rest of your week. Close now.